Okay, so that's just introducing the terms that we're interested in: estimator, estimate, and sampling distribution. We now want to talk about methods of estimation, and I want to introduce two very commonly used methods to construct estimators. These are methods that can be applied quite generally and can be used to perform inference with respect to multiple parameters using the same random sample. And throughout the discussion that we conduct now, we're going to suppose that we have a random sample X from a population with a joint density fx given theta, and that a sample has been observed. So real data has been taken and there's a realized observed samples from this random sample. And we'll start by talking about methods of moments estimation. That's our first estimator. And this is a very simple estimator that simply tries to use the sample moments derived from the sample, and equates them to moments derived, or the theoretical moments of a distribution, let's say. So let the jth moment of the distribution be denoted by this expression here, and you should be familiar with this because we talked about it in the last lecture. So u prime j equals the expectation of random variable x to the power of j. And the jth sample moment is defined as the average of each observed data item to the power of j. Okay, so that is essentially using an average to approximate that population moment. Okay, so if that just equals 1, that's the expected value of the distribution, and we would be using the sample mean to approximate the expected value or the mean of the distribution, the population mean. So mj is an estimate of u prime. Sorry, m prime j is an estimate of u prime j, and m prime j, the method of moments, is given by that expression here. That's the estimator because it's in uppercase. The estimate is in lowercase because that's based on real data. So let's just look at a concrete example. What we've just said is method of moments estimation. It's one of the simplest estimators because all we're doing is matching the theoretical population moments to the sample moments. The population moments will typically be a function of θ1 to θk, say, giving in most cases k equations in the k elements of the vector theta. And the method of moments estimator solves this system of equations for the parameters in terms of the moments. So let's look at how it works. Here we're going to look at an example from the normal distribution, normal method of moments. Suppose we have a random sample that are IID normally distributed with mean mu and variance sigma squared. Then θ1 is equal to mu and θ2 equals to sigma squared. We want to set the sample moments equivalent to the population moments. So m prime 1 is equal to the sample mean. M prime 2 is equal to the average of xi squared. Okay, that's just defining the moments in terms of the sample counterparts. So u prime 1 is equal to theta, that's mu, and u prime 2, the second theoretical moment of the distribution, can be written in terms of theta squared plus sigma squared. Now, to get that expression, that's straightforward. If you go back to last week and look at how we wrote an alternative formula for the variance, we said the variance can be written as the expected value of x squared minus the expectation of x squared. So that's how, if we add this expectation of x, square it, and we add it to the variance, that's how we get the second moment of the distribution. So solving this for theta and sigma squared yields our methods of moments estimator. We're going to say our estimate of theta is the sample mean, and our estimate of sigma squared, we're going to use this expression here, is written like this, and gets us to this moment of estimator, method of moments estimator for the variance. Okay, let's look at another example of method of moments. In this case, we're going to deal with a binomial method of moments example. So consider a binomial random sample taken from a binomial distribution with size n and parameter p. The population moments derived from first principles or from the MGF can be written as follows. The expectation of x equals n to p, and the expected value of x to the power of 2, the second moment, is np times 1 minus p plus n squared p squared. That's easy to derive. All we need to do for the method of moments to get our estimates is set these equal to the corresponding sample moments and solve for n and p. So we're going to use the sample mean and set it equal to np for this one, and we're going to use this expression here and set it equal to this quantity for the second moment. Solve for n gives us this expression here, and solve for p would give us this expression here. And you can go through this in your own time just to convince yourself that this is indeed the case. But the method of moments really is as simple as that. It's an easy to implement method, but it's not always optimal. For that reason, not always used, because the sampling properties of the estimator can often be improved upon. So we'll turn now to a second method of estimation, which is probably by far the most popular method used to derive estimators, and you'll come across it in this course at various points in the course and actually in your professional life. And it's based on the concept of maximum likelihood estimation, based on the concept of likelihood function, introduced by the statistician Ronald Fisher. So this concept of a likelihood function really is key to understanding maximum likelihood estimation. And we'll define it here in definition 11. The likelihood function for parameter theta and data small x, denoted L open brackets theta x, is defined as this function here, viewed as a function of theta for fixed x. This is really important. This is not a probability density in x given parameters theta. This is a function of theta given fixed data that we observe, small x. And if the random sample we're dealing with are independent, then due to the laws of probability and the laws we looked at last week of joint densities, we can write the likelihood function over all observations as the product of fxi for theta. So that's the likelihood function. Maximum likelihood function is very simple. What it's going to do is the maximum likelihood estimator is going to find the estimate theta hat x that's for which the value of the likelihood function is maximized over the parameter space with x held fixed. So maximum likelihood estimation then is simply the parameter point that maximizes the likelihood of obtaining the data. It's the parameter point that maximizes the likelihood of obtaining the observed data as measured by this likelihood function, as measured by this probability, essentially, joint probability. So it's often easier actually to maximize the log likelihood instead of the likelihood itself, because the log of x is a strictly increasing function of x. The maxima of both the likelihood function and the log likelihood coincide exactly. So sometimes rather than using maximize the likelihood itself, we'll maximize the log likelihood. It can make matters simpler in particular cases. So the maximum likelihood estimate then, maximum likelihood estimation procedure works as follows. First, we write down a likelihood function, and we'll look at an example specifically of how that looks in a minute. We take the natural log and collect terms involving theta. We then seek to find the value of theta for which the log likelihood is maximized. For instance, let's say we've got a k-dimensional parameter vector. We solve the k-simultaneous equations by setting the partial derivatives equal to 0, the usual way we would for an optimization problem. And then we check that the estimates obtained in step 3 is truly a maximum and not a minimum or some other point by inspecting the second derivative of the log likelihood function. And so we have to be alert to cases where the likelihood is not differentiable or when the maximum occurs in the boundary of this parameter space, but otherwise that is the general procedure we use for maximum likelihood estimation. So let's look at two simple examples. First is maximum likelihood estimation involving a Bernoulli distribution, so Bernoulli likelihood. Suppose we have a random sample x, x1 up to xn. These are IID Bernoulli distributed with parameter p. Then we can write the likelihood function for parameter p given observed data x1 to xn as the product of those terms there. And if you just go back to the notes from the last lecture, you'll see that that is the probability distribution, of the Bernoulli function. It can be written also in this form. We take logs and write the log likelihood in this form, and then all we need to do to get an estimate of parameter p is differentiate this expression and set the result equal to 0. And then we get this expression here, set equal to 0, multiplying through by p1 minus p, cancelling terms and rearranging, gives us this solution for parameter p. So that's the maximum likelihood estimate. We can verify that the second partial derivative is negative and therefore that we have found a maxima. And in this particular example, it's somewhat easier to differentiate the log likelihood than the likelihood, illustrating why we use the log likelihood in rather than the likelihood, as it makes the matters easier in certain situations. Okay, second example of maximum likelihood estimation. We're going to look at a normal likelihood. So again, we have a random sample. We're assuming they're IID, normally distributed with mean mu and variance sigma squared. Then we can write the likelihood function for x1 up to xn for our observed data as the product of the normal density. Here it is here, so the product of a normal density. And again, we'll take logs and write the log likelihood function in this form. We now want to estimate the value of two parameters, mu and sigma square. So we're going to partially differentiate. It could be either, but we're going to use here the log likelihood. We're going to differentiate with respect to mu and sigma square and set the value equal to 0. So what we're saying is we want to maximize the likelihood as given by this density, the product of these densities. We want to maximize the likelihood of observing the data. Want to maximize the likelihood of observing data in the parameter space. What parameters correspond to the maximum likelihood of observing the data? That's what we're trying to do. That gives these expressions here, and just bit of algebra. We find the solution to these equations are that our estimate of mu is the sample mean, and our estimate of sigma square is given by that expression there, which is actually the formula for the population variance, not the sample variance, and we'll return to this later. The maximum likelihood estimate of the variance is in fact a biased estimate, but that's the estimate it gives us. And again, taking the second partial derivative, we find that's negative, and therefore in each of these cases we can verify that we have found a maximum.